thank you. Sarah, originally, 3 years ago, reached out to me, and I'm glad she finally arrived. I'm glad that you guys are back on track, and I'm glad you had a very good day today with your event. I feel a bit like I've crashed the party, actually. It's very lively. You're clearly all happy, so that's great to see. I also assume that you've been exposed to a huge amount of deep tech. So this talk is non-complicated. Okay, just to allow you to wind down a bit. Also, thank you, John, for introducing me, and Simi for likewise hosting. It is a great pleasure to be invited to talk to this august group in this august university. I know it's august because my daughter plans to come here next autumn. Not to do EEE, despite my best efforts. Right, as John said, I am a chip designer. Always processes, actually. I've been doing it for nearly 40 years now. The only time it's ever worth building a new microprocessor is where some enormous change happens. Some big market emerges. So the arrival of the internet, for example, as a commerce mechanism, demanding broadband service to homes, the arrival of cellular communication, the arrival of multimedia. Crikey, some of you are probably too young to remember. There was a time when images and videos and music was not processed by digital computers. It wasn't that long ago. And now, kind of probably the last 5 or 6 years, AI. AI is the biggest single shift we will ever see in computing. It's probably the single biggest event technologically humans will ever encounter, if it succeeds. It happens to have arrived at a time when our main technology for doing computing, which is silicon, is running out of steam. So this talk is a little bit about that. What do we need in order to be able to execute AI, sort of hopefully to extract its full potency to improve our society? And what's in the way of doing that with silicon? And you know, what compromises might we make along the way? Okay. So I start off by quoting this chap, who's actually Polish originally, but he became naturalized Brit. He worked with Tommy Flowers on the original Colossus computer in Bletchley Park, and with Alan Turing up there as well. He was a statistician by background, I.J. Good, some of you may have heard of him. He was a very early thinker about the idea of mechanizing intelligence. Published a number of works, but in one of them he asserted, it's probably his most famous work, he asserted it was vitally important for the survival of humanity that we build a machine cleverer than us. I think the reason for his assertion was that he felt that without advice from superior intelligence, we might screw it up. Actually, on his death, well, posthumously, his assistant claimed that towards the end of his life, he started to have doubts. He thought actually the last thing we should attempt to do is produce a more powerful intelligence than ourselves, because we'd probably create it in our own image, and that would probably be a disaster. So I leave you to make your own judgment. However, I introduce this quote because it defines nicely what we mean by ultra intelligence, something that is unambiguously smarter than a person. And obviously, the whole endeavor of attempting to harness artificial intelligence is to achieve that objective. Actually, there's a corollary objective, but I'll come around to that. So first of all, we're going to try and define intelligence. Here's my really start. No one can agree what intelligence definition is, so here's my attempt. The ability to produce responses to stimulus, so a black box stimulus in, response out, that are useful, based on imperfect knowledge, because no intelligent being in the real world can ever have perfect knowledge. And importantly, to improve that response with experience. And that simple definition leads to two results, if you like. First of all, if you're going to generalize, then you need a model. Because how else are you going to do it? You've got to build a model from the knowledge you have, and then you've got to use that model to produce responses where actually you don't have any knowledge, using your judgment. So there must be a model, and a model is something that has structure that translates input data to output data. That's what I am, that's what you are, that's what an AI is, translator input to output. And the second thing is this adaptation behavior. So that says that the model must be parameterized, and those parameters must be learned. What are they going to learn from? Well, templates, obviously. So AIs always have two modalities, if you like. One is you provide input, they use their knowledge to produce a central output, which might be useful. And the second is they have a feedback loop where that output is not good or could be improved to tune their own parameters. But the point is, from a computing point of view, we have a model structure and we have some parameters. Now, there are two types of computers. If you're going to build a computer that's really valuable, there are two types of computers that might be valuable. And only one of them actually needs to be smarter than a human in this sense. So this is a sort of concept that's well embedded in high performance computing. There are capability machines and there are capacity machines. Many of them, sort of Google and Azure and AWS data centers, are capacity machines. They're not sort of single powerful computers. They're warehouses full of computers that can do useful work cheaply. And there will be scope for AI capacity machines, things that can do jobs that bore humans, frankly, and maybe do them better. But even if they didn't do them better, it would be good not to bore humans. And we hope it'd be cheap as well. And then there are capability machines, and these are ones that try to do things humans can't do. Try to be ultra intelligent, superhuman. They don't actually ever, of course, need to be as general purpose as a human. They don't need to worry about food, probably. They don't need to worry about sex or relationships or politics. Well, maybe politics, actually, you probably do need to worry about politics. So they'll never be quite the same as humans, even if we tried to make them that way, and never have our learning experience. We're going to focus on these capability machines, because I think the capacity machines are just trickled down versions of capability machines. The capability of an AI is determined by a couple of things. First of all, its design, and secondly, the amount of effort taken to educate. They're a bit like children. If you start off with a good design, you've got a better chance the educational effort will be worthwhile. But without both, you're not going to get very far. In the sense of an artificial intelligence, the educational effort is a function of the amount and quality of the data that you have to learn from. And it's also a function of the scale of the model. There are a number of parameters, and this will be a recurring thing. And then the design is about at least a couple of things. First of all, how efficient is the representation of data that you're trying to learn from or produce? And that has been a subject of much study in the early days. We now have quite a good, easy form of representations. And then the second thing is the effectiveness of the processes that you use for training and inference. Right, where are we today? These lovely graphics are produced by our head of software, who's also our chief artist in Graphcore. These are actually computational graphs of real neural networks. This one is large, spread over 4 of our processor chips during training loop. I've blown up a bit of it, but even there, you probably can't see. If you can see little speckles, each tiny dot, probably doesn't have enough resolution. But if you can see a tiny dots with tiny filaments, each of those dots is an independent program written in C++. It's atomic in the sense that it has all its data at the beginning of its run, it will run to completion and will produce a result which can be inspected by another independent program. And the filaments represent the flow of data between these programs. This is a simple neural network. This is a little language modeling thing. Simple by today's standards, quite powerful, but simple. It has millions of component programs. So imagine a software system in which just one program to do one job for one purpose actually consists of millions of component programs in C++. So that's kind of interesting because it means, first of all, you can't write it. It's beyond human authorship. Secondly, you can't debug it. How are you going to open a million debug windows and look at what's going on and things don't fit immediately? So it's beyond human inspection as well. Really, really fundamental change to the nature of writing programs on computers. We effectively have to write at the program generator level. We have to use tools to inspect things for us. Each of those millions of programs potentially gets spread over, or never one chip. Nobody ever trains any sort of AI now on a single chip. They train on tens or hundreds of thousands, tens of thousands of chips. In the future, you can expect them to train on millions of chips. Each individual component program in that diagram of millions is typically executed 1 million times in order to learn. The hardware story is not much simpler, a lot more metal work in it. We make chips. This is a floor plan plot on the left. Yeah. On the left of our Mark II Colossus processor, a 59 billion transistor beast. It has many individual processors on it, all executing those little program threads. It's packaged in that silver box. Anyone's a aficionado of this. There we are. It's about 1.25 inches square, which is as big as everyone else's chip now. All fab optics are limited to this size, 33 millimeters by 26 millimeters for the enthusiast. No one can make a chip any bigger than that, and that is precisely as big as 2 nanometers. Questions what you put on top of it. We put 4 of those chips in a 1U, a 1U, that's probably techno speak, inherited from age-old telecommunications racks. The height dimension in a computer rack is measured in rack units, RUs, and they are 1.75 inches in metric. So our box is 1U high, about 2.5 feet deep. 4 chips and a lot of cooling equipment. And then we put those into racks. So typically 6 and 4 chips in a rack, and then we build machines in many racks and yada, yada, yada. So there can be trillions of transistors at play, trillions, even approaching quadrillions of transistors, running for actually sometimes months to train one model once. So running a single program, in some cases, can now take multiple millions of dollars. That's assuming you have access to a machine that costs multiple tens or hundreds of millions of dollars in the first place. To run one program, to learn once. Here's our chip. I thought I'd put this up to the silicon enthusiasts so you can get your bearings. 59 billion transistors, 7 nanometer CMOS, 14 metal layers defined by 86 optical masks, about twice that number of steps in the fab, photolithographic steps in the fab. As I say, it's a full reticle design in about 8 square centimeters. It has nearly 1,500 independent processors. Each of those processors actually is a sophisticated vector and matrix machine that can run 6 independent programs, so about 8,000 independent programs running on one chip. Every processor can communicate with every other processor through this massive exchange crossbar in the middle, 11 terabytes per second, non-blocking communication between processors. This is the sort of stuff that we'll take a warehouse not that long ago. Now it's on a chip, and we're filling warehouses with chips like this. It's not possible to make a chip this size and run it fast in a synchronous way, despite the fact that all of our design know-how and desire is to design synchronous machines. So we compromise. This is actually mesynchronous, by which I mean, as far as any particular point on the chip is concerned, it is synchronized with all these things. However, as we go across the chip, the precise definition 3 o'clock in the afternoon gets smeared out. So 3 o'clock in the afternoon in the southwest is not the same as in the northeast. It's like an early, like a current day version of early railway time. The exchange fabric I've drawn in pink in the middle is that interconnect, the tile, tiny little tile we might be able to see in blue. That is a processor with about 624 kilobytes of RAM attached to it. About half of the diode is RAM, random access memory, static random access memory, and there's nearly 1 gigabyte of random access memory. So this is actually the world's highest performance AI chip in production today, at 350 trillion floating point operations per second. The floating point operations are all very low precision, 16 bits. Characteristic of AI, so you don't need much precision. And about half of the die area is SRAM, which makes it also actually the largest SRAM chip ever built, even though half of it's not SRAM. And it's made by TSMC in Taiwan. Very, very, very impressive and competent company. Right, let me flip over to AI a bit. So basically, the bigger the model, this is our learning so far. We might discover something next week that turns this on its head. But so far, the bigger the model, the more potent the AI. It sort of makes sense. It's a general rule of computing that the amount of memory you've got access to determines what you can compute. And the speed of the machine only determines how fast you can compute it. So ultimately, if it's a question of what can be computed, then memory always trumps performance. This is certainly true in AI so far. This is, I've stolen these pictures from a very recent blog by Google, and again, a couple of days ago. What's this model called? This one's called PaLM, Pathways Language Model. That stands for. There's a reference to it there. The interesting thing is that our experience of scaling up AI, even as we know it today, which is relatively simple structures of neural networks trained with single data modalities like images or sentences, is that as you scale up, you go through these thresholds where new behaviors emerge, new capabilities. The breakout of deep learning really could be sort of, well, this breakout of deep learning, especially one in the 60s or one in the 80s. This one, the successful one, could probably be pinned on the emergence of a thing called AlexNet that could recognize people in pictures or cats in pictures. And that was like an emergent property. It's like, oh, that's really surprising. How does it do that? Different set. But the fact that it could do this was emergent, and it only emerged at scale. Well, there are other properties that we now know emerge at scale. In other words, bigness doesn't just give you more ability to do the things you know you can do. It actually, you go through these thresholds where you can suddenly do new things. And here's a lovely example. Sense of humor. At what scale would you expect an AI to develop a sense of humor? This is an example of that, exactly that language model I showed on the previous graph, explaining a joke. It's a terrible joke. It's very geeky. It's explained in a very deadpan, non-humorous manner. But nevertheless, surely, if an engineer can explain a joke in fluent prose, this is straight out of the machine, then it must have understood the joke. So it must have a sense of humor. Isn't that extraordinary? I mean, you have just trained this thing on sentences. It has learned not only grammar from those sentences and how to generate these sentences, it has learned the semantic content of the stuff it was exposed to a level where not only can it answer questions, but it can explain concepts like, why is something funny? That is quite extraordinary. Right, let's talk about that superhuman intelligence, ultra intelligence. Having positioned parametric scale, in other words, the amount of state in the box is more important than the number of floating point operations it can do, for example. Let's think of it with reference to the brain. So a human brain has somewhere between 100 and 1,000 trillion synaptic weights, apparently. I'm surprised it's not more tightly bound than that. Perhaps you could ask your colleagues in the wetware part of Knowles at some point why they don't know that number more accurately. But apparently, according to Wikipedia at least, and I did try and find other sources, but was unable to bound it any more tightly. So, order 100 trillion, maybe more. The technology is pretty unreliable. We know this using damaged brains, and yet they can recover very well. And it's just Knowles die all the time. So it's obviously got a lot of redundancy. So you won't need all of those weights. You probably just need most of them. And we also know from some really fascinating work on this, at least the synapses in the hippocampus, that they have a resolution of about half a byte, at least in the hippocampus they do. There are many different types of synaptic neurons, so maybe others have more or less. We also know structurally that the information that's learned by one synaptic connection can't be used by another one somewhere else. In other words, you can't do weight transport, and therefore you can't use these learned weights in a convolutional manner, which is what all artificial neural networks do today. Every artificial neural network today depends heavily on convolution. In other words, it reuses its learned state in many places. And a human can't do that. So a human is presumably parametrically less efficient. Sorry, yes, a human is parametrically less efficient than artificial neural network in that sense. So therefore, conclusion, implementing a machine capable of ultra intelligence, unambiguously clever and human, might only require about 100 terabytes of data to be learned and stored. Now, I can buy a 100 terabyte disk drive, they're actually quite large. But at least if I had a handful of disk drives, I can store a whole lot of human on that, which is worth a thought. Maybe I don't even need that much because of the redundancy. Where are we in the sort of discovery of mechanisms to actually harness AI? Well, the results might surprise you. First of all, we do have a general representation now of different types of data. So in other words, we can build neural networks, artificial neural networks, that can handle text or sound or pictures or graph structures of molecules on the same fabric, like your cortex does. So that's the first thing. The second thing is that we have at least a sort of Lego set of types of structures that allow you to build effective neural networks. So there's a sort of emergence of at least aspect of general structure of the model. Thirdly, we have a master learning algorithm. A learning algorithm that's applied to all forms of data and all types of artificial neural network today and work. And then fourthly, we are in a position where the parametric scale is starting to decouple from the compute scale. So in other words, I can have a big neural network and it's lots of information without it necessarily having to be big in terms of lots of compute. And this is vitally important, as I'll come back to. Right, so elements of a general model. First of all, representations. So we can take pictures and chop them up into patches. We can take sentences, chop them up into pieces of words. We can embed those tokens, as they're called, in a vector space. In other words, the concept cat is a point in a very high-dimensional vector space. The number 3 is a point. A patch of pixels around that have a particular pattern is also a point. And each of those vectors is represented by a bunch of very small floating point numbers. The second point is transformation between input and output best occurs over many layers. In other words, don't try and do it all in one leap. Do it in lots of layers, incremental change. And each increment should be additive and not multiplicative. This much we have learned. Residues, they're called. And then the last couple, well, it turns out to be useful to alternate between mixing up the components of a vector, or the internal elements of a vector, and mixing up between vectors in alternate layers. And there is at least some evidence that isotropic networks are a good idea. In other words, all layers are basically the same. There's some evidence of that in your cortex. It has layers which are similar, so they're not exactly the same. But it is interesting that they are so similar, and that it appears that the same is true in artificial neural networks. Now, I said there was a master learning algorithm. There is. It is stochastic gradient descent, enabled in particular by back propagation of gradients. First order stochastic gradient descent works for everything. All sorts of people have tried all sorts of higher order learning mechanisms. None of them so far compete with this. This is used in 99.999% of all AI today. It's robust. And it has some interesting properties for the machinery, unfortunately. First of all, it has end-to-end sequential dependencies. So if you look at the left on the top, data comes in, and at each stage of processing interacts with local weights W. Layer by layer, you get to the end, you compute some error function, and you feed it back. And you feed it back, as you feed it back, you compute gradients with respect to those activations, and then gradients with respect to the weights, and then you can update weights. And because the processing has to walk all the way down the end, do some evaluation, and walk all the way back out again, before the next data can come in to benefit from the updated weights. You can't pipeline a structure like that. It's a disaster in hardware. I wish the algorithm engineers who very cleverly came up with this had come up with something different. But they didn't, and this works. So the hardware has to adapt to this. It is possible to pipeline a structure like this to use batches. But it's not easy to pipeline a structure like this. The second thing is that the major data flow is all explicit, it's all laid out. In other words, a compiler can see that. It knows when to move data about. So if, like me, you spent 40 years engineering microprocessors, you'll know roughly half the effort that has ever gone into designing good microprocessors has gone into making caches and branch predictors successful. Automatic caches and automatic branch predictors. They are not required for the major data flow here. So all that stuff's out the window. The compiler can do it all. And then thirdly, and this is a really good one, we need to do about 1 million iterations. And in each iteration, you need to read all the wait states, do some calculation, and then write it all back in. And unfortunately, that means that you cannot store the model on a solid state disk. So when I said earlier, I can get 100 terabytes of solid state disk in my hand, unfortunately, that's no good. Why can't I? Because solid state disks wear out. They wear out with a few thousand read-write cycles, and you make a million just run the program up. So they can't live in solid state disks. They have to live in DRAM or SRAM, and that's quite a lot more expensive. That human parameterization of about 100 terabytes, well, it's about $4 a gigabyte is the real sort of hyperscaler price paid for DRAM today. So you do the math, quite a lot. And then the other thing is, unfortunately, that if you have to do 1 million iterations and every one of them has to read all the memory and then write it back in, if that takes 1 second, then it's going to take you 12 days to run through it. Okay, if you're learning a bit more, that might be a certain people are waiting longer than that. But it's not a short amount of time. So you don't really want it to take a lot more than a second to read and write memory. You might wish it was a tenth of a second. You certainly don't want it to be 100 seconds, otherwise it will take years. So therefore, if you have 100 terabytes, unfortunately, you also need about 100 terabytes per second to it, which is not a characteristic of the very large memories currently built into very large computers like servers. You can buy a server with a terabyte of memory, but it will not have a terabyte per second of bandwidth. So that aspect of building conventional machines is broken as well. Right, let's look at what's been happening in silicon. So this is the functional density. There are 2 plots here. One is for a pair of logic transistors that are used to make cells, gates, and things like that. Generally treat them as pairs because you've usually got a vertical arrangement on a P transistor and an N transistor to make a CMOS device. And then the black line is the density of SRAM, so static RAM cell, 6 transistors, standard structure. You can see that they have both been improving very nicely, 2,000x increase in functional density over the last 25 years, but the wheels are starting to fall off the wagon now. SRAM has basically stopped. So there won't be any more process nodes for the benefit of getting more SRAM in a square-inch facility. The gates have not quite stopped yet, but they're going to. They're going to heel over just like SRAM had. So how many more process nodes will there be? Today, the most sophisticated process node in production is 5 nanometers. It's a half nanometer, it's kind of half a node away from 7. But 5 nanometers doesn't mean anything, by the way. It's just a label. There will be a 3 nanometer node in a couple of years' time. There may be a node after that, probably. There may be nodes after that, but they won't be. They won't have the characteristics that we associate with traditional Moore's law scale. In other words, twice as many transistors at the same power and same cost. So that's going to be a problem. And partial response to that problem is the packaging of many silicon die together, rather than this sort of thing. This is one die, actually, isn't it? It's a trick. There's actually 2 ways, one on top of each other. This is the world's first wafer-on-wafer microprocessor. So, I'm sure you know, these chips are made, first of all, on 12-inch wafers. And then the wafers sawn up to make the chips. Chips are tested. Good ones are put into packaging. So, This thing is made by taking two of those wafers and gluing them together before you store them up. In fact, a bit more complicated than that. So they're joined together by hydrophilic action. It's essentially a cold weld between microscopic landing pads on each of the two wafers. So there are no bumps or anything, which means that the interconnect between them can be very, very, very fine. So I can use it to get a lot of signal through. And then the second thing that happens is I then thin, using a chemical mechanical polisher, I thin one of the wafers down to about a third of the thickness of the cling film. It's completely transparent and it would wall about if you were to react. I can only thin it that much because it's attached to the other wafer. Why do I do that? Because I then want to drill using an ion etcher holes from the backside through to the interface between the two wafers to make contact with the active devices at that interface. And that process, known as backside TSVs, backside through silicon vias, is ultra precise because I have to stop within a couple of nanometers of the right point. So I've got to drill through some microns of silicon contact with my ion etchers at maybe 1 million points. And every one of them is stopped exactly at the right point. Otherwise, you just punch a hole through a transistor or something. So very, very sophisticated process. And the start, so this one actually we bond a logic wafer to another wafer that uses DRAM technology and is just full of DRAM bit cells used as capacitors. Turns out it's our highest density planar capacitor. Why would you do that? Well, because it smooths out the power supply. This chip tends to try and chop between demanding no amps and demanding about 500 amps from a 0.8 volt power supply, or roughly a nanosecond, half a nanosecond basis, and that's problematic for keeping the voltage at 0.8 volts. But if you attach one of these wafers to it, it fixes the problem. So on the left, bottom left, is an example of something similar. That's called a chip on wafer. You can probably see this is an AMD processor. There's an I/O die in the middle on a package substrate with some processor dies either side. But on top of the processor dies is a small die, actually a cache SRAM die. And that is actually placed on the wafer as chips before the processor wafer is sewn up. So that's a chip on wafer process. The one in the middle, that's a Tesla AI chip. That is actually a reconstituted wafer. So take a wafer, chop it into chips, work out which ones work, put the ones that work back into the position they would have been on the wafer, but in some magic glue, harden the magic glue. You have a synthetic wafer. The great property of this particular magic glue, it's called integrated fan-out info. The great property of this particular magic glue is it's so much like a wafer that you can now pass it back into the fan and do some more metallization or whatever else you want to do. Fabulously powerful technology. It's been used in your phones for years, but never at scale more than about a square centimetre. Now we can use it 12 inches across, and we'll see people doing that. And then on the top, various other tubes of placing multiple silicon die next to each other in order to try and minimize the interconnect energy and maximize interconnect bandwidth between them. So edge as butting, whereas this technology, very far away, will be used for vertical passing the interconnect. The one in the center middle, by the way, is the most ambitious of those. This is Intel's new Ponte Vecchio GPU. It has 2 silicon substrates on top of an organic substrate, and each silicon substrate has 21 chips in it. And then additional to those, you've then got 8 stacks of high bandwidth memory, each of which is 9 die deep. So it's like an entire factory's worth of silicon put on one device. It will be economically ruinous. They will make that thing to show off, well, I don't know, to show off, but actually it won't make much commercial sense. But you know, it's all we're exploring what can be done. So that's the alternative. So as we can't get more and more transistors on die, you'll see that happening. In other words, dies assembled closely together on substrates to create the effect. yeah, minor digression. So if I build an ultra parallel machine, in other words, I start building dies with thousands of processors on, and then assemble those dies into objects that we maybe millions of processors on eventually. How do I maintain program order? Well, it's one thing to write a program and make sure it's correct, but how do I maintain the order between the components of the program? And how do I avoid being swamped by the communication resources required for all those component programs to talk to each other to get the job done? First of all, here is the software abstraction that we use for the Graphcore process. Now, IPU, it's called. So it is a graph, which is what we call graph. The graph has two types of nodes. It has nodes that are data and nodes that are processing. The processing nodes can contain some state as well, but the point is, by distinguishing these two different nodes, we can be very efficient with them. But apart from that, it's an arbitrary graph. You can have loops, all the edges are directed, you can have loops. And the processing nodes basically take as input stuff that comes from the data nodes and then write as output to the data nodes. And they can slice and dice information from the data nodes at will. Each of those blue processing nodes executes what is known as a codelet, which is an independent atomic program. It takes the input data, it runs to completion, doing whatever it requires, writes the output data, job done. And then usually the whole sequence of the graph is iterated in order to converge to some criterion. The entire program runs on the chips. So the host hardly does anything. These things are all accelerated chips to a host, but the host doesn't really do it. So how do we maintain order with that software model on a multi-processor chip like one I'm showing you earlier? The answer is we used a paradigm that was actually invented in 1990 by Leslie Barron and Bill McCall, Oxford. And it was used to synchronize workstations in arrays of workstations. It basically works by alternating or repeating a sequence, which is do local compute on data you already got, synchronize with everyone else, and wait for everyone else to be ready. Then exchange data you need for your next compute phase, and as soon as you've got that data, do the next compute phase. Why do we use this? Well, first of all, I explained the graphic on down below. So the pink stuff is compute, the blue stuff is exchanging information, and the yellow stuff is waiting for other people to synchronize. The vertical axis is the 1500 tiles on a chip, and the horizontal axis is time. And this is just a tiny fragment of learning a neural network. And you can see the alternation between synchronize, exchange, compute, synchronize, exchange, compute. No phase takes longer than it needs to operate. The compiler is responsible for trying to make sure that the yellow stuff, which is wasted time, doesn't dominate. In other words, load balance the machine. How can it do a good job of load balancing the machine? The answer is because the data flow is explicit, because we have the master rather than SGD. So it doesn't have to guess. The compiler can see what's going to happen next. Yeah, a little bit of nitty gritty there. The interesting thing about this BSP process is the fact that it serializes communication with computation, and yet we've all spent the last 50 years trying to overlap them. So is this a good idea? Well, the answer is it's a good idea in an energy limited world. Because if I overlap them, all that would happen is the energy consumed go up and I have to slow them down. So I can get into that in post discussion, but it is actually efficient to serialize if you are energy limited and to parallelize if you're not. Right. The other nice thing about BSP, actually, I should just pause. The other nice thing about BSP is you cannot write a program with a concurrency hazard. I used to work for an old British company in Bristol called Inmos, We made a thing called a transceiver in a language called Opera. And I can assure you, if you tried to use more than about 3 processes, it was painfully easy to write programs with concurrency hazards. So deadlocks, livelocks, races. That used CSP, communication sequential processes, as its protocol of communication. And I'm glad to say you can't do that with BSP. It's concurrency hazard. Right, back to silicon. So the previous slide showed what was happening to density. This one shows what's happening to power or energy per operation, and it's much, much worse. So Moore's law scaling is at the bottom left. Things got better every year, fast. We reached a point at 90 nanometers in 2005, where we could no longer scale the voltage by enough to maintain that. With each shrink in geometry, what you want to do is you want to shrink the voltage by the linear shrink dimension amount, so roughly 0.7 linear per node, so 2x area, 0.7 reduction in voltage, in order to maintain that slope. Unfortunately, that ended. We've been slowing down the scaling of voltage since then, corresponding considerable decrease in the improvement in energy efficiency of operations. And we are now entering an era of constant voltage operation. What does that mean? It means that the cost of doing flop in joules is going to be constant now. So if you want to do more compute, it doesn't matter what process you use. If you want to do more compute going forward, you will have to burn more power, which is unfortunate, isn't it? Because we're now ever more focused on not burning power, doing this sort of thing. So the only way around that, there is no answer in certain. The only way around this is not to do as much compute. And you remember I mentioned earlier, we've reached the point where we now separate the parametric scale of the neural network from the compute scale. So this is good. We can build more powerful AIs with less compute. That's exactly what we need. And if we don't, we'll be in trouble. What are the limits on the energy of computation? Some of you, I'm sure, are experts in this field. So there is a quantum mechanical limit characterized by Landau in the 1960s, I can't remember. He observed that if you destroy or erase one bit of information, then that loss of entropy must result in an energy cost. And the energy cost is defined by the loss of degree of freedom. It's characterized as kT log 2, where K is Boltzmann constant, C is absolute temperature. 2. So it's about 3 zetajoules of room temperature. And what do I mean by erase a bit? Think of it not so much as sort of flipping a bit in a memory, but like a 2-input logic gate, like a NAND gate. That has only one output. You can't construct the 2 input states from the 1 output state, so therefore you erase a bit. You can build reversible stuff, and this doesn't apply to reversible stuff, but nobody's managed to do that in an energy efficient way either. An electron, a single electron, is a charge of about 160 zepto coulombs. And the smallest net, the smallest piece of wire between 2 transistors or 2 gates in a modern circuit, like a 7 nanometer circuit, has a capacitance of about 1 femtofarad. It's about as small a capacitance as you will ever see. Obviously, if you've got a long wire, it will be much bigger. 5,000 transistors, roughly, hold that bit at 0.8 volts on that net. So if you took those 5,000 transistors, electrons away, took 5,000 electrons away, you'd flip the bit, you'd destroy it. And it turns out that that cost, in other words, removing the electrons, is a much, much bigger limiter to the energy efficiency of silicon semiconductors. Well, in fact, of anything operating at that voltage than the Landau limit. So quantum mechanics doesn't stop it, but the number of electrons will. How many electrons could we rely on? They're quite energetic electrons. In my experience, they're not very reliable. they jiggle about, they wander off. I don't know if you know, but one of the things we have to really guard against when making chips is a thing called electromigration. It is like it says on the tin. So you have a long piece of wire on one layer, and you wish to go down to a different layer and maybe go in a different direction. The electrons come zooming along this piece of wire, and some of them do that. Some of them don't. They go barreling off the end. They're unable to corner fast enough. They go barreling off the end into the direction. they're using drags and metal material with them. And what you end up with is the end of the wire grows over time. And eventually it will meet some other piece of wire and produce a short electron migration. So electrons, don't trust them. They don't do what they're told, they don't do what they're supposed to. They have a mind of their own. And if you've got 5,000 on average, they'll do what they're supposed to. But I reckon if you went down to 500, they probably wouldn't. So we're not that far away, I think, from practical thermal limits at room temperature on the energy of an operation. I know from speaking to John earlier that he's an expert in cooled CMOS, so that might be the right answer. And that graph there is really to explain to you why we can't really reduce the voltage much anymore. Basically, because the speed comes down to the threshold, intersect with the speed graph, which is the black one, sorry, the red one. That's related to the threshold voltage of effect, which in turn is related to band gaps. And it's not much we can do with that. So if we're dependent on electrons and silicon, then these things are pretty set in stone. So if we went much slower, we could go much slower and be more power efficient, but it would cost a fortune in silicon material. So we don't want to do that. If we would go much faster per transistor, we'd burn an enormous amount of power. So we don't really want to do that either. For that reason, everyone has settled at about 0.8 per volt. And that's where we're going to stay. And at 0.8 per volt, we will dissipate about 1 picojoule per floating point operation. And just to demonstrate the point, here is a breakdown of the energy consumed when doing big convolutions on the tile processes of the IPU pattern chip. So you can see that much of it is in the floating point data path. We spend some energy moving data to and from the memory. In our case, remember, the memory is very close, so that energy is minimized. And then there's a bit of background energy described as then not in other words, that's the energy the processor burns where in fact you do no operation, but you're still moving. Right. So, yeah, last couple of points, I think. GPUs have been adapting to become better at AI, being AI processors for about 10 years. They started with graphics processors, of course, AI came along and tried to be good at that, so they have adapted. It's educational to discover that actually they've got 300 times better in 10 years at AI workloads. NVIDIA, in their last graphics technology conference, claimed it was 1 million times better. I know Jensen ran quite well, so that doesn't surprise me. But the real figure is 300 times, which I think is no less impressive. Where did it come from? Well, about half of it, 16x, came from smaller numbers. Smaller numbers, fewer bits, burns less energy. Simple. The fact that you're doing matrix operations rather than vector operations actually gives you like a square benefit on the dimension of the number as well. So you get 16x from roughly a 4x reduction in number width from 32 bits to 8 bits. The second thing is improvements in process. So roughly 8x came from 28 nanometers to today's 5 nanometer processor. And then of the rest, 1.7x increase in clock speed, but at the cost of nearly 3 times the power. So probably wouldn't want to go much further in that direction. And then finally, 1.4x for improving the architecture. Not much. What happens next? Well, the first one probably doesn't go any further. I don't think we'll go below 8 bits. Maybe we'll go to 4. Exponentially spread 16 codes as a 4-bit number. Doing AI with 8 bits is hard. 16 bits is easy. 8 bits is hard. 4 bits probably not. I've already shown you that the second one's not got much room to go. The third one, well, yes, you can have more speed, but only if you want to burn exponentially more power. And the one that must yield for us is the last one. We must build new architectures which start off from a better point. And obviously that's what Graphcore and others are trying to do. And just to calibrate you, these are real numbers. So 1 billion transistor language models today would need to be trained on about 20 billion tokens, according to the latest research, in order to be optimal. In other words, that's the right ratio. If you didn't have that amount of data, then you should produce a model of a different size. Train it on a different amount of data. So 1 billion parameters today, 250 chips, about 100 kilowatts. for an hour. You go up by a factor of 1,000 to a trillion. Then unfortunately the data needs to go up as well. So everything goes up to square. So 25,000 chips, a 10 megawatt supercomputer. And then it still take you a year. So to get to human, remember you got about another 100x in scale, which is 10,000x on these numbers. So 10 megawatts for 10,000 years? Is that what you want? It's not going to work very well, is it? So what's the secret? Well, the secret is brains do routing. So when you see something, when your synapses fire in your retina, they do not, those signals, that incoming data does not interact with every single synaptic connection in your brain. It doesn't cause all of your neurons to fire. If it did, your head would probably melt. Maybe if a tiger was to come on the stage now, quite a lot of neurons would fire, but not all. In other words, your brain manages to steer incoming data to the synaptic connections where it's actually landing. And the good news is we have discovered how to do that for artificial neural networks. I say we, I had no part in it, but I have a follower. And it's obvious, isn't it? Suppose you build a big language model and you train it off the internet. It's going to learn about French and Russian and German and English. It's also going to learn about politics and art and science and all sorts. So probably. And then you give that language model some data, you give a sentence query. It's obvious, isn't it? It's not going to need to use all that data. The sentence is going to be in one language or another. It's going to be about one subject or another. So you should be able to steer to just a subset of the learned information that is useful. And these are called routing networks. And this is the third breakthrough that we're currently going through in AI algorithms. Really, really important for the machines on which they run. So the first breakthrough was the emergence of deep learning. In other words, the realization that layered structures of incremental transformation could produce surprising results, intelligence-like results. They needed curated data. They needed, in order to recognize a person, they had to get huge label pictures of that person. So the scale of those models is limited by the cost of curated data. That was the first era. The second era came on a few years later when we worked out how to train in a self-supervised manner. In other words, you didn't need curated data, you could just read Wikipedia. It's basically done simply by masking stuff out and then predicting what you mask out. Because you have ground truth, you don't need a supervisor. That allowed model scale to expand from a few 100 million parameters to a few 100 billion, which is where we have been for the last few years. Routing is the next breakthrough, the last one we need. What limits the growth of models before routing came along is the cost of compute. The fact that every incoming data has to interact with every parameter of the model, so you get this exponential growth in compute cost. Now with routed networks, that's no longer the case. So prospectively, this hasn't been achieved yet. But we have already got examples of a 50x increase in the scale of model for the same compute, usefully. Prospectively, we get 1,000x. And then we'll just be limited by the cost of memory, because we will have decoupled the compute. It'll just be limited by the cost of memory, and that's where we want to get to. That takes us to human scale. And these networks already exist, and they already work. I'll skip that one, that's a little bit involved. Human scale. We could build a machine, we could start now, build a machine with the parametric scale, or a machine that would support neural networks that we know to work, with parametric scale of a human being. 100 trillion parameters, or thereabouts. It would be about this big. It's quite big. It's about 100 square meters of warehouse space. 68 of those racks that are 7 feet tall. You consume 2.5 megawatts, which is much less than some big supercomputers. Cost about $50 million. Same applies. It would have about a petabyte of DRAM in. You need rather more than just the weight state and the optimizer states as well. So you need about 10 bytes per parameter in the model. So a petabyte is good for 100 trillion parameters, probably. And you need that DRAM to be accessible within a second. So petabyte per second order, likewise. And incidentally, in order to achieve that, you need only about 2,000 processors. And from those 2,000 processors, you could reasonably get about an extra floor. Is that enough to do what you need to do? Well, like I said, and it determines how fast you become intelligent, doesn't determine how intelligent you can be. An extra floor is certainly quite a lot of computing. And it requires the balance between the data access bandwidth and the compute rate determines the amount of convolutional reuse you need to achieve, about 5,000, which is a very reasonable number for a neural network. So, to sum up, AI is huge. I don't think there's a single aspect to computing which will not, as already, have some element of learning integration into it. It's an obvious paradigm shift. Rather than humans having to solve every problem that we wish a computer to help with, and to codify our solution as a program, we get the computer to help solve the problem in the first place by giving it examples and letting it learn like we do how to solve problems for examples. And unfortunately, it arrives this huge opportunity. It happens to require huge compute, and it arrives just when we can't have any more compute from silicon, unless we do things differently. And the energy limitations are various, but actually the ones that matter are now basically constant. So we're not going to get any more juice really from process technology. Probably just get cheaper and cheaper chips, but they won't be any more powerful. So we've got to work out how to harness hundreds, thousands, millions of chips of roughly the same energy efficiency as they have today. And if we do that, then an ultra intelligent scale, parametric scale, is feasible today. Expensive. Of course, building that machine doesn't mean you've delivered an ultra intelligent computer. That's how we talk about it. But at least you've delivered a computer that's potentially capable of it. And finally, the only way to improve things, is to redesign how we do computing, to redesign how we write software. What does software mean now? It doesn't mean we write a program that codifies a method of solution. That's nasty software. So redesigning the software stack, redesigning the hardware stack in concert with the algorithms. Remember I said the master algorithm for AI is a disaster to a machine because of the sequential dependencies it embodies. If that isn't the end game, if there is a better algorithm out there, then for heaven's sake, let's design it alongside the knowledge of the computers and their energy efficiency and other limitations. So there has never been a better case or a stronger case for co-design. And just as a PS, because I know today's the day of light, and I know that you've had something with a theme about light coming in today. So I always get asked about light. Will that help? Can you use photons instead? And my answer is always this: a computer consists of 3 boxes. There's a data path that does that. There's a memory, and there's a controlling engine that decides what to do next. And always these new technologies focus on the data path first. And there are photonics structures which allow the data path to be much more efficient. So there are semi-quantum. But without access to memory, that will be a Canadian. And we know we can make the memory out of silicon, and it doesn't consume a huge amount of power, just have it sit there remembering things. But that interaction between the world of photons and the world of silicon, that will need to be energy efficient, and that's always the problem. And fast. If you build them really fast photonic data. Anyway, that was just a thank you.
Thank you for fascinating lecture. I think you have a few minutes for a Q&A and a voting microphone. So please pop your hand up if you have a question. And while you're thinking of that, I'm going to kick off and talk a little, ask about power. Because you gave a very interesting comparison with the brain, and there's sort of 2.5 megawatts of power, and I think our brain is 50 watts. So there's about 5 or 6 orders of magnitude there. What's the brain doing in terms of power efficiency?
Yeah, it's embarrassing, isn't it? So people always point to spiking communication. There's a big difference. It must be truthful. I always say that. That can't be it, right? Evolution is a ruthless optimizer. And I can immediately improve the energy efficiency of a spiked communication system by replacing it with one that uses steps. In other words, a spike is 2 edges. I don't need 2 edges to transmit it, I need 1. So why hasn't nature done that? Well, so I don't think it's the spike in communication. It's definitely the case that your brain uses electrons in the same way as our silicon uses electrons to move information about. So it's not that. In fact, if you look at the sort of wire structures we build, the silicon chips, we build all sorts of different thicknesses of wires and all sorts of different screen arrangements, depending on the trade-off between speed and density. And it's exactly the same in the brain. You've got fat axons and thin axons, you've got thick dielectric and thin dielectric, and they have different speed and energy properties accordingly. So that's the same. There may be some processing going on in the neurons, which is more efficient than what goes on in our logic clusters. Everybody know. We certainly had some fascinating conversations with some academic researchers. Simon McLaughlin at Cambridge was a zoologist. Spent a good number of years looking at a particular molecular mechanism in the visual cortex of the fruit fly, and have managed to isolate a state machine. It's literally a few proteins that kind of interact with each other. And it's got a handful of input wires and a handful of output wires and a handful of states. And by moving into this, it's amazing, absolutely amazing. Is that more efficient than doing it with electronics? Well, I don't really know, maybe. So I think the crux is the brain clearly has a very different architecture. It uses charge transport to move information about, so we haven't got that wrong. But I'm pretty sure that there must be something in its architecture that we've got wrong. Its learning algorithm is definitely different. Its inference algorithm is probably different. That's definitely different. Yes.
Very impressive numbers, but can I ask your opinion on consciousness? Do you ever think that consciousness will remain in the organic level, or is there a pathway for it to develop in hard matter?
Well, I think all I can point to is the evidence that some surprising human characteristics have emerged as we have moved stepwise towards human scale. My personal expectation is that all human characteristics, all characteristics of human intelligence are achievable by mechanism. In other words, I don't think there's anything special about us at all. I think we are machinery. We're not silicon machinery, so we're different machinery, but we are machinery, and whatever we can do, other machines built with different technologies could potentially also.
Hi. So given the urgency of climate change, and that's not, I mean, national that you developing resources so much power, what are companies like Graphcore actually doing to be as sustainable and energy efficient as possible?
Sorry, I missed the last bit.
So what are companies like Graphcore and other companies are doing in order to be as energy efficient as possible?
So there isn't a day when I don't try and work out how to make our systems more energy efficient. Not least because that's obviously the right thing to do from a business point of view, but also for some views, and I quite like it. However, I think the easiest answer to that question is the technology can help answer. In other words, by producing machinery which is more intelligent, more capable of solving problems than humans, perhaps we can give it the problems that really matter, like climate change and like curing all disease. It is a bit of a punt. You know, we may just find that we've burned enormous amount of energy trying, but we're going to get there. I sure as hell hope that doesn't happen. Maybe one more question.
Hi, thank you for the really interesting talk. You kind of touched on it just at the end, but what's your thoughts on what your company think, I guess, about us moving away from transistor-based computing in terms of seems to talk about how separation of learning and process and implementation and human brain is kind of integrating in a very different way from where we are. Do you think about that in terms of future work?
Well, I mentioned that my daughter was going to come to this August institution. She's going to do biochemistry. And her simple statement to me was she's doing biochemistry because obviously electronics is now very old-fashioned. And we'll soon be computing with engineered chemicals. So I hope she's right, but I'm going to have to leave that to her because I don't really understand how that works. What I can tell you is it's taken an awful long time and trillions of dollars of investment to get to the point where we can bang out silicon chips with tens of billions of transistors that work again and again and again for a few tens or hundreds of dollars. So the factories that do this work are works of art. They cost about $20 billion now to make. There are precisely 3 factories in the world that can make state-of-the-art chips, but we could make some more if it's worth it. They are incredible cathedrals of human engineering achievement. And they're supremely economically efficient. So any new technology has got to be not only better than a transistor, a silicon transistor in theory, but it's got to get to that point of economic maturity before it runs out of funding. And I just think that's an impossible hurdle unless something really fundamental changes. And of course, there will be fundamental change. These things occur, like silicon replaced valves, relays. But you can usually see those things coming. And I do spend quite a lot of my time looking out to the horizon. I can't see anything coming. I don't think there's anything that could replace silicon as a computing substrate for humanity within the next 30 years. Doesn't mean we shouldn't try now, but I can't see it coming. Caveat optics and quantum in the data path, if you can do the energy, the conversion well, or come up with a correspondingly massive cheap petabyte scale memory that we want to. Anyone for a quantum petabyte scale memory? Are we working on that?
That's really good. Well, thanks very much. I should just make a few closing remarks to thank Simon properly. I think we've been treated to a really fascinating and a very pedagogical introduction to ultra-intelligent AI and the challenges associated with realizing such a process in silicon. We've heard everything from the emerging capabilities of AI, as trying to scale, which is it's a fascinating concept of building computers without being fully aware of what new powers each generation is going to possess. I personally had a full-on geek out listening about the state-of-the-art waveform die bonding methods. I remember learning when I was 13 about adding decoupling capacitors, and I never imagined that the lengths with wafer bonding of CSV that you can go to just to smooth a power supply. So that was fascinating, and then that ranging to these 42 die assemblies named after 14th century Florentine architecture. And then we heard about the Landau limits and how many electrons, apparently only 5,000.
Always gets you in these.
Apparently only 5,000 electrons used to store bits today. We've had different evolutions of neural networks, from deep learning to self-supervision to new breakthrough of routing. And at the end, I was just thinking about this sort of quote. It was a very now famous quote from I think the late 1940s that said that computers in the future may weigh no more than 1.5 tons. And there was a quote I think that you said, Simon, ultra intelligence might require less than 100 terabytes of learned state. I just wonder whether in the future that's going to be one of the quotes, but I think for now it seems that computers are weighing around 1.5 tons. So that quote's come back. We can use. But let's thank Simon again for